First, let's talk about design challenges. Statistically, battery fires are less prevalent than engine fires. However, battery fires are harder to put out and less predictable. In fact, 30% of the time when BEVs catch fire, they're parked and not charging. Consequently, fire protection has become the first design challenge for battery packs. To reduce fire risk, cells should be kept cool and thermally insulated. Typically, thermally conductive materials are used to bond cells to a cold plate or a cooling ribbon, while thermally insulative materials are used in case of fire to limit propagation. Therefore, a thermal management strategy is needed, which incorporates multiple materials. Battery fires can occur due to manufacturing defects or mechanical, electrical, or thermal damage. Although NMC cathodes are more sensitive to elevated temperatures and have higher energy densities than LFP, all lithium cells pose a fire risk. Some of the events that can occur were captured at 3M's battery lab. For example, we saw large flames, rapid temperature increases, hot gas particles, and smoke generation. Therefore, OEMs need to incorporate thermal management materials and undergo pack level testing to ensure battery packs are as safe as possible and comply with regulatory requirements. The second design challenge is battery pack weight. According to vehicle breakdown data by A2Mac1, the relative weight of a 2018 Tesla Model 3 is 300 kilograms higher than a 2018 Honda Accord, most of which is attributed to the battery pack. Essentially, the battery pack weighs about twice as much as an engine and transmission. As a result, lightweighting solutions are sought to minimize the negative effect of pack weight on range. Today, to address automotive design challenges, potting and encapsulation compounds are applied to cylindrical cells, which improves thermal uniformity and reduces the risk of thermal propagation by minimizing thermal effects on adjacent cells. These compounds are made of either polyurethane, acrylic, epoxy resin, or silicone, and are low viscosity to facilitate potting of non-standardized cavities. We see polyurethane and silicone foams as the most common in the field. On one hand, the polyurethane can offer structural benefits, while on the other hand, silicone is safer, multifunctional, and easier to use. In fact, last year, Elkem received an R&D 100 award for its patented BlueSil RT foam for electric vehicle thermal management. Again, why use silicone? Well, silicone is non-hazardous, has zero reaction byproducts, and emits a non-toxic smoke when burned, making silicone a safer choice. Silicone potting compounds are also multifunctional. First, silicone is an excellent insulator, both thermally and electrically, which helps insulate cells from the inside and outside. Second, silicone is an excellent sealant. It's non-corrosive and adds protection against moisture and coolants. Third, silicone can dampen vibrations, increasing interconnect durability. From a processing standpoint, silicone is much easier to use. Silicones quickly wet out most surfaces, cure at room temperature in minutes, and have insignificant exotherms. Further, Elkem's battery foams are non-expanding, which helps achieve uniform cell coverage and greatly limit cell movement. Most impressively, Elkem's solution is proven with over 5 years in OEM production, during which time we've helped put 2 million battery electric vehicles on the road with over 60 billion miles driven and zero failures.